Hello everyone, I am Meenakshi Chauhan and in this video I am going to discuss about Carry-lookahead adder. In this lecture I will be discussing about basics of binary addition, what is ripple adder and what are the drawbacks of it. Next, how a carry-lookahead generator will solve the problem of ripple adder. And next, how a carry-lookahead adder is designed. So let's get started. Before studying carry-lookahead adder, it is strongly advised to students that the students must go through the concepts of half adder and full adder in depth because half adder and full adders are the basic building blocks for designing parallel adders. So let's have a quick introduction of half adder and full adder. Then we will understand the n-bit binary addition. Binary addition of 2 bits. Half adder is a circuit that adds 2 bits. As you can see here, the circuit diagram of half adder is given, the block diagram of half adder is given, and the truth table is also mentioned here to recall the concept of half adder. Half adder adds 2 bits, bit A, bit B. 2 bits can have 4 combinations 0, 0, 0, 1, 1, 0, 1, 1. And the corresponding sum and carry value is also mentioned in the truth table. 0, 0 will produce sum 0 and carry 0. Addition of 0, 1 will produce sum 1, carry 0. Addition of 1, 0 will produce sum 1, carry 0. And addition of 1, 1 will produce sum 0, carry 1. Next, binary addition of 3 bits. As we know, full adder is a circuit that adds 3 bits. 3 bits can be A, B and C in. 3 bits can have 8 combinations. And the addition of 0, 0, 0 will produce sum 0, carry 0. 0, 0, 1. It is the value decimal equivalent of this addition is 1. So it will produce sum 1, carry output 0. And next 0, 1, 0. Sum is 1. So it will produce sum as a 1. 0, 1, 1. The decimal value equivalent to 1, 1 will be 2. So it will produce sum as 0, carry is 1 because 2 is represented as 1, 0. So sum will be 0, carry will be 1. Next 1, 0, 0. The sum will be 1, carry will be 0. Next 1, 0, 1. Same concept will apply. That sum will be 0 and carry will be 1. Next 1, 1, 0. Same concept will apply. Carry will be 1 and sum will be 0. Here 1, 1, 1. The decimal equivalent for this addition is 3. So carry will be 1 and sum will be 1 because in binary the representation of 3 is 1, 1. So sum will be 1 and carry will be 1. And you can recall the circuit diagram of full adder here. It takes 3 inputs and produces sum and carry as an output. So you must learn about the expression produced for sum and carry out. Now binary addition of two 4-bit numbers. Here we have two 4-bit numbers x and y, and we have to perform addition of these two numbers with y bit. So x0 and y0 will be added and produce sum as s0 and carry output c1. The c1 carry will go to the next stage and c1 will be added with x1 and y1. And the addition of these three will produce sum as S1 and carry output as C2. This C2 will go to the next stage and will be added with X2 and Y2. The addition of these three bits will produce sum as S2 and carry output as C3. This C3 will again go to the next stage and will be added with X3 and Y3. It will produce sum as S3 and carry output as C4. So in this way, you will notice that the addition at one stage will produce a sum and the carry output will always be feeded into the next stage. So here at every bit position or stage we have 3-bit addition. One is number X, second Y, then 1 bit coming from the previous stage. So we have written here a carry input and carry output. Carry output denotes the carry produced by the addition of at particular stage, or we can say ith stage, and that carry output will go to the next stage to be added, and this time this carry will be carry input. So we have carry output which will be carry input to the next stage. Initially there is no carry input, so by default C0 will equal to 0. In this way, we can calculate binary addition of two n-bit numbers. So we have two n-bit number x and y. The addition of these two n-bit numbers will produce some n-bit sum and n-bit carry output. For designing a binary parallel adder, what we expect that the adder will take n bit of first number, n bit of second number, and then it will produce the sum of n bit and it will produce the final carry. Let's have examples of binary addition of two n-bit numbers. So here in first example n equals to 4. So we are performing addition of 4-bit numbers. 4-bit number x and y. In first example x is 1101, y is 1010. We will perform addition bit by bit. So 1 plus 0, sum will be 1, carry will be 0. This carry will go to the next stage. So this 0 carry will be added to 0 and 1. The sum will be 1, carry again will be 0. Again carry will go to the next stage. Here the addition will be performed, next sum will be 1 and carry will be 0. Then carry again will go to the next carry will go to the next stage. Here 1 plus 1, the sum will be 0 and carry output will be 1. In the second example, we have taken 5-bit example. We have two 5-bit numbers x and y. We will perform addition bit by bit. Here 1 plus 0, addition will sum will be 1 and carry will be 0. The carry will go to the next stage. Here 1 plus 1, the sum will be 0 and carry will be 1. Here 1 plus 1 plus 1, the sum will be 1 and carry will be 1. Carry will go to the next stage. 1 plus 1, sum will be 0, carry will be 1. Again carry will go to the next stage. 1 plus 1, sum will be 0 and carry will be 1. In this way, we can perform addition of n-bit numbers. Ripple carry adder. From the previous example, we understood that the carry generated at one stage will go to the next higher stage. Following the same concept, a ripple carry adder is designed. Here, n full adders are cascaded to create n bit parallel adder. So for designing n bit ripple carry adder, we require n full adders. N bit numbers and full adders are required. And these n full adders will be connected such a way that the carry output of the stage I is connected to the carry input of the next stage I plus 1. Here the carry output of one stage will be connected to the carry input of the next stage. Therefore, sum and carry at stage I plus 1 cannot be produced until the input carry from stage I occurs. So, and as you can see here in this example that the two numbers are being added with input carry and it produces the sum as 0 and carry C1. And this C1 is connected to the next full adder. Here, this full adder will not produce the valid sum until C1 comes to it. So, it is making the statement that sum and carry at stage I plus 1 cannot be produced until the input carry from stage I occurs. Whenever it will not get the carry input from the previous stage, it will not produce valid sum and carry. So this carry propagation from one stage to another is called carry propagation or ripple carry. And this propagation leads to a significant time delay in addition process. And this delay is called carry propagation delay. So due to the propagation of carry, some delay is introduced in producing sum and carry at higher stage. So this delay will be called as carry propagation delay. As you can see here, for n bit number, n full adders are required from 0 to n minus 1. The final carry Cn will be produced by the last full adder in a ripple carry adder. A ripple carry adder is also known as n bit parallel adder. From the previous example of n bit parallel adder or n bit ripple adder, we can design 4 bit binary parallel adder. For 4 bit numbers, we require 4 full adders. Think in such a way that the carry output of one adder is going to the carry input of the next higher adder. Here, all 4 full adders are taking one bit of x and second bit of y and producing sum and carry as output. Due to sequential propagation of carry from one stage to another stage, this ripple carry adder has some delay and it has delay in producing carry output of 2 delta, where delta is the delay of basic gates, and how this delay for carry is produced as 2 delta. As you can see here, the circuit diagram of full adder, you will see that the carry is generated after 2 level of gates. Here inputs are given and here carry output is generated. From input to output, it has 2 labels of gates. Delta is the propagation delay of a basic gate. Here the carry will be generated after 2 delta. As you can see here that the inputs are given here and sum is being produced here. So from input to sum, it has 3 labels of gates. So the delay for producing sum will be 3 delta and for carry it will be 2 delta. So delay in producing carry output will be 2 delta for the first carry, and the delay for the carry C2 produced by the second full adder will be 4 delta, and so on. Delay for Cn will be 2 into n delta. Here we can say that delay is proportional to n, the delay for carry. Here after C0 or these inputs, the C1 will be produced after 2 delta. Next, this adder will also take 2 delta to produce carry. So this C2 will be generated after 4 delta. Next, this adder will also take 2 delta to produce carry further. So it will take 6 delta. Next, C4 will be produced after 8 delta. So from this example, we can say that delay is proportional to number of bits n. Now let's understand delay for sum. As we have seen that sum is produced after 3 delta. So here the sum at next stage will take 3 delta to produce sum, and the 2 delta the carry from the previous stage. Next, as we have seen that C1 will be generated after 2 delta. So S1 will be generated after addition of x1, y1 plus C1. Now we look at the delay for sum. As we have seen in the previous circuit diagram of full adder, the sum will take 3 delta delay to be produced. Now delay for S1 will be the sum delay plus delay of carry 1. As we know from the previous example of carry delay, C1 will be produced after 2 delta. So sum will take 3 delta to be produced. Total it will take 5 delta. Next, C2 will be generated after 4 delta delay. And at this stage, the sum will be produced after 3 delta. So the total delay will be 7 delta. The delay for stage n minus 1 will be 2n plus 1. So this is a very long delay due to the sequential propagation of carry from the initial stage to the final stage. The propagation delay in ripple carry adder is very large. So this is the drawback of ripple carry adder, that it introduces a very large delay in producing carry and sum. So let's discuss the drawback of parallel binary adder. As we have seen that ripple carry adder introduces a large propagation delay to produce the output, so it limits the speed of adder. In worst case, the carry ripples through all the stages. The total delay is proportional to the number of bits. So as the n increases, the propagation delay also increases. So it will degrade the performance of parallel adder. In real life, we design 32-bit adder and 64-bit adder. So in 64-bit adder, the propagation delay will be very high. Carry-lookahead adder solves the problem of carry propagation delay in ripple carry adder. So how does a carry-lookahead adder solve this problem? So it solves the problem by calculating the carry signal in advance based on the input signal. As soon as these inputs are given to the adder, it starts calculating the carry signals to be generated at each stage. So once it has the carry calculated, then it will use all the carry signals in the addition process. So it will reduce the carry propagation delay. So all the carry bits for the previous stage are generated in parallel before actual addition start. So it will calculate the carries in advance. After the initial delay, all the additions can be done in parallel. Once it gets to the all carry signals, then the addition can be performed in parallel. Now we have full adder circuit with the help of two half adders. As we know that in ripple carry adder, at each stage a full adder was used. We have seen the delays in carry output as well as some output to be produced. So here in this diagram you can see that there are two internal signals, one is PI and second is GI. So PI is defined as AI XOR BI. Here GI is defined as AI into BI. Sum SI will be PI XOR CI, where the carry output, final carry output will be here Pi into Ci plus Gi. So in this way we can define the sum and carry output. Why we are doing this? Because these sum and carry equation will help us to design the carry look ahead adder. Before going ahead, we first look at what is carry generate function and what is carry propagate function. Carry generate function represents the condition when a carry is generated at stage I, independent of other stages. So carry generate represents the generation of carry at particular stage I, because GI, as we have seen that GI is defined as A into B. If G is 1, GI is 1, it means the carry has been generated. And when the G will be 1? When A and B both will be 1. So the carry will be generated when GI is 1. And what is PI? Propagate the carry. Carry is propagated when PI is 1. PI is what? P is A XOR B. It will propagate the carry at stage I to next stage I plus 1. So as you can see in this truth table, in final carry output, there are 4 ones present. So for this combination, it means G equals to 0, but P equals to 1, because 0 XOR 1 is 1. So it will propagate the carry to the higher level, apply to the next stage. Here in next record, you will notice that 1 0. So P will be 1. Here same, the carry will be propagated. Carry will go to the output. In next stage, here A G will be 1 because 1 into 1 will be 1. So carry generated. Here carry will generate. As you can see, input carry was 0, but due to the inputs, the carry will be generated. Next, here G equals to 1, so it will generate a carry. So carry will be generated here. So carry generate and carry propagate are those functions. Basically, carry propagate will propagate the input carry to the next stage, where carry generate function will denote the generation of the carry at that stage. So according to these two equations, we can design n-bit carry look-ahead adder. So in this example, we have taken 4-bit carry look-ahead adder. For 4-bit, I will be 0 to 3. So for each value, we will calculate the equation of S as well as carry output. So in this carry look ahead adder, we always concern with the carry output. So because we have to reduce the carry propagation, we have to calculate the carry in advance. So we will consider the carry output equation. Here the carry output equation is Gi plus Pi into Ci. So we will put the values of I and we will solve the equation. After solving these equations, we will get C1 equals to G0 plus P0 into C0. Here C2 will be G1 plus P1 into 0 plus P1 into P0 into C0. As you can see that C1 is depending on C0, which is the initial carry, and it is 0. So there is no matter of carry propagation here. Now in second carry, now in C2 we have removed the dependency of C1. So we will not have any carry input here. As for C3 and C4, we have removed the dependency of input carries. So according to these equations, we can design the circuit diagram. Here the block diagram of 4-bit carry look-ahead adder. Here we are adding two numbers, 4-bit number A0, A1, A2, A3 and B0, B1, B2, B3. So we will calculate Pi values and Gi values. Here at the first level, as soon as we will have some input A and B, this circuit diagram will calculate Pi values and Gi values. Some carry look ahead mechanism will be used here on the basis of previous equations, and then this circuit will produce C1, C2, C3, C4 in parallel. And by using these carries, we can calculate some output as well. Here we have detailed design of carry look ahead adder. So in this you can see that as soon as the inputs are given, the Pi and Gi values are calculated. Here in second level, an carry look ahead generator circuit is used to calculate the carries. So as you can see that these circuits are based on the equation input. Here as you can see that C1 equals to G0 plus P0 into C0. So Here you will notice that the circuit diagram for that equation was made, as according to equation C1, C2, C3 and C4, the circuit diagrams are made. Here this circuit is called carry generator circuit. This first level will calculate PI and GI values, which is independent of carry inputs. Next level will calculate the carry signals as soon as PI and GI values are calculated at each stage. Now, once the carries are available, the sum will be calculated. So you can see here the first level include delay of delta, because here you have one level of gates. In this carry generation circuit, you have two level of gates. So you have two delta delay here. And next you have one level of gates, so you have delta delay. So in this adder, only 4 delta delay is produced to get the output after applying inputs. So in this adder, you may notice that the delay has been reduced, but the hardware circuit has become very complex, because we are using gates to calculate the carries. So here time will be reduced, but the hardware circuit will be very complex. So why carry look ahead adders are required? Because as we know, addition is the basic operation, and this addition is used in various arithmetic operations such as subtraction, multiplication, division. Speeding up our arithmetic operations, we need a carry look ahead adder, because it reduces the carry propagation delay of a ripple carry adder and provides you the faster addition. So in digital circuits, speed is a major concern. So the carry look ahead adder gives the faster calculation or faster addition, but on the other hand, it has a complex hardware circuits. So far, we have discussed about the basic of binary addition, where we recall half adder, full adder, and then we started discussing n-bit binary addition, where two n-bit numbers were added. Next, we look at the ripple carry adder and the drawbacks associated with that adder, where the carry propagation delay was the major concern. Then we look at the concept of carry look ahead. Then we looked at the carry look ahead concept to solve the problem of carry propagation. Then we designed then we discussed how to design a carry look ahead adder. See you in the next lecture. Till then, happy learning. Thank you very much.